So we're going to be talking essentially exponential growth is a main application, week 9. So we're going to be talking about logarithmic examples, exponential growth, like bacteria population, interest calculations, and hopefully we'll get to the number e and the natural logarithm. So these have like logs have practical applications. If you like radioactive stuff, if you keep this radioactive stuff at home, and one such application is radioactive decay. For example, carbon dating. Has anyone ever watched like an archaeology show on TV? Archaeology? I took like an archaeology course in undergrad. And for a field trip, we went to someone's house that actually discovered a pharaoh in Egypt and made a lot of money because they brought it back to Canada, and the government of Egypt wanted that pharaoh back and paid them like $10 million for it, and they ended up very wealthy people. But so archaeology does this thing called carbon dating. And it can determine like the age of an item. Anyways, here's some background music too, if you're watching this from home on YouTube. I should update my list. Anyways, what is radioactive decay? So scientists measured that starting with a large quantity of radon atoms, let's say you have a large amount, after 92 hours, half of the radon atoms transform into plutonium atoms. So like these elements get transformed. We can introduce this concept called the half-life of radon. So this means essentially, so the half-life of radon is actually 92 hours. So what does this mean? So let me double check something. So essentially half of it depreciates in 92 hours. So if you have 100 atoms in 92 hours, you have 50 atoms. Half of it gets cut down. So each radioactive isotope has essentially this concept called a half-life. Carbon dating is probably the most famous one. Anyways, let's look at this. So for example, the half-life of plutonium is 238, an isotope. So it's just an isotope, essentially. This is not a chemistry class, don't worry about that. And it's approximately 88 years. So if you, let's say right now, you have some plutonium in 80, or let's say at birth, you had some plutonium when you were born, and 88 years later, you would have half of it. You would have half that amount, whatever you begin with, is the idea. So it's basically, let's go back here. So this half-life is essentially time. So it's a time factor because you notice it's in hours. So 88 years later, you have essentially half that amount of those atoms or elements that you have. So we could kind of understand this, and we could draw a picture. So let's say here, X is radon. Then one half-life later, let's say here, X is divided by 2. That's the amount of radon you have. So this would be half of the amount. So half is basically lost. And this is, we're starting at time equals 0. And so T equals 92 hours. Now another half-life, I could color code this. So this is again one half-life. This is another, let's say we take another half-life. Well, then the time would be, from the beginning, would be 92 plus 92, taking 2 half-lives, so that's 2 times 92. And this would be, so you would have, you began with x divided by 2, so half of this is lost. And we have x divided by 4, right on. And we can continue with this pattern. So x divided by 4, we're going to lose again another half. Of this amount. And we have x divided by 8, this amount left. And at this particular time, it would be, time would be 3 times 92. This is just another half-life. And remember the half-life here of radon is 92 hours. So from this diagram, you should be able to see like the generalization and the pattern that's sort of forming. Here we could kind of see from 1 to 3 half-lives, x divided by 8, well, that is x, the amount that we originally began with, times 1 over 2 to the power 3. They're the same thing. So we can kind of see this, where this 1 over 2 to the k comes from. So what's here in this box that I'm drawing a box around. So if a radioactive isotope has a half-life of h time units, so like these are our time units, let's say 92 hours, then after k times h, sorry, I should write this a little nicer. K times h, time units, the number of atoms of this isotope. So the amount is basically reduced to 1 over 2 to the exponent k of its original quantity. So it's reduced down by like this factor. So we start with, right in red. So this KH amount, K times H, and goes to K. But we're just going to make a substitution for KH as time. And it's going to go to and divide by H. And it's the same thing, essentially, as this picture. is the next formula. So essentially you can generalize this previous fact into like this following and relate it to what we just drew into this. So if a radioactive isotope has a half-life of H units, time units, then after T time units, the number of atoms of this isotope is reduced to this factor, this 1/2. And then the exponent, instead of before we said it was K, this exponent is T divided by H, which is this, of its original quantity. So essentially, we're just making a substitution. It's just the same thing as what we just drew with like this picture, which is, I think, a little easier to understand. But we're substituting this K in for this. It's a little bit more straightforward if we just see an example too of how to use like this formula, what it means. So suppose you have radium 226, and it has a half-life of approximately 1600 years. So that's our half-life, H. I always like to take out information, years. If you initially have 1,000 units, so initially our initial quantity is 1,000 units, how much of it will be left after 500 years? So what is the quantity after, or 50 years, sorry, after 50 years, where this is our time, 50, after, sorry, left after. So using the formula, so after 50 years, the quantity is reduced. To basically 1/, looking back, so we have our H, we have our T, so we have our T and our H, 1/2, and this is half-life. So it's split in half, so this is why we have that 2. To the exponent, so it goes up top, the T first, so 50 divided by our half-life, which is 1600 of what it originally was. Which was 1,000 originally. So therefore, the leftover quantity is basically 1,000 times 1 divided by 2, this number. You would need a calculator for this. So you would use a calculator and get 978.57. Use a calculator, basically. Write that down. And so that's the amount you reduced. So with carbon dating and things like that, all living, I won't get too much into it, but when you're alive, you have so much carbon and then you start to lose it. And so when you find something, you can date how old that item is about finding how much a quantity of that carbon it has, and then you can figure out the age of something. but I won't get too much into it. So we just showed for radioactive decay, just to review what we just did, the half-life is for radon is 92 hours. And we just learned that after T time units, a radioactive quantity reduces to 1/2 to the power T over H of its initial size, where H is that half-life. So we just learned that. So a question, how long does it take an initial amount of 100 units of radon to reduce to 30 units? So we have 100 and we want to find the time it takes to reduce it to 30. And we know the half-life is 92. So we know the half-life, H, is 92 hours. So we want 1,000 units times this factor that reduces it down. So 2 to the exponent T over H is equal to 30. Let's color code it. So this 100 is the initial amount. And this 30 is our final amount. So essentially, we now just rearrange and kind of solve. We know what H is. So we can isolate for T and solve. So this would be 100 times 1 divided by 2T divided by 92 equals 30. You could divide by 100 on both sides if you wish. You get 1/2 the exponent T divided by 92 is equal to 0.3. We could rearrange it if we wish. So 2 to the exponent negative T over 92, and just bring it to the top. Okay. Now we could take the log of both sides, because now it's something we're talking about logs, so we can relate it to something we know. So take the log, because it's 2 to the exponent of something. So let's take the log. This implies the log, and we could say like base 10, and you take the log of both sides. So the log 2 to this exponent, negative T divided by 92 is equal to the log of 0.3. We can bring this exponent out front. Times the log 2. And then we can, of course, divide by the log of 2 on both sides, which implies negative T divided by 92 equals this, log 0.3 divided by log 2. We could calculate like this with a calculator. Negative 1.74 is this value. This implies negative T over 92 is equal or approximately equal. That's why I can put 2 lines and a dot or 2 squiggles to mean approximate. Your choice. Negative 1.74. And then we can multiply both sides by negative 92. Implies our t here is equal to negative 1.74 times negative 92, negative make a positive. So it's approximately 160 hours. So that's the amount of time it essentially takes to go, yes? The 92 hours, this is given back here. Radon, it has 92 hours. So, and we're looking at how much radon it asks. So that's the half-life, and that's given in the question. So that's, so essentially to review, we have to basically isolate. We have an initial amount, and then we have a final amount. And we're trying to figure out the time. So we see if it were 1 half-life, well, it wouldn't be 1 because then you'll get 50, like 100 would go to 50 in 92 hours. 50 would go to 25 in 184 hours. Here we have 160 hours, which kind of makes sense just as a check. Like, does this answer make sense to you in terms of the half-life? Do I have a reasonable answer? I'll just review one of the questions from the assignment about logs. So if log of A equals K, it's 1.2, let's say, and log of AL equals 3, let's find log of A times KL. And what is the formula for this? Log of A, the quotient. All you do is separate them out using that product rule. The product rule, turning it into the sum. We have like this is equal to 1.2, and this is equal to 3. So therefore, this is going to be 4.2. This is what we did before. I'm just applying it. So this was the product rule. This was the quotient rule. Log of AL minus this. So this is 3. This is 1.2. So the answer would just be 1.8. So that's just a review of what we just kind of did. So exponential growth. So a function is said to have this exponential growth if this function is of this particular form. F of x is equal to c times b to the exponent kx, where c and k, they're just positive numbers, and b is greater than 1, like it could be. and X is our variable, essentially. So this is our exponential growth formula. So there's other equivalent forms of exponential growth. This isn't the only one. This is just one of many. For example, any function, let me write it out. So let's say f of x is equal to cb kx. So you could say, you could just basically make a substitution. Like for small b is equal to b to capital B times k. So just make the substitution if you wish. You could just rewrite it using your rules of exponents. And this part is equal to b. So it's something of this form, like basically C, K, B, they're all constants essentially. And X is that variable that changes on that X axis. So this is essentially, is an exponential. Let me see if I can clean this up. Our growth functions. One possibility. Okay. So basically, like these functions, they increase very rapidly, right? And this is, we can think about like what was happening like when the virus first, COVID first began, right? Like it sort of took off like wildfire, right? It was exponentially increased all of a sudden when it first began. So every function with exponential growth increases more rapidly. So it goes faster, essentially. Everyone more rapidly than every polynomial, in the sense that if this function with this exponential growth, if you have one, and a polynomial, then this function f of x is going to be greater than this polynomial for sufficiently large x. So it just means as x approaches infinity, this happens. So the value of f of x will eventually beat the value of p of x. So like these exponential growth functions increase so rapidly, graphing them in their usual manner can display too little information. So it's difficult to actually scale these. For example, this function, let's say f of x, where 5, let's say, times 10 to the exponent x. Well, if we try to graph this, like a quick sketch, when x equals 0, okay, well, 10 to the power 0 is 1, 1 times 5 is 5. 10 to exponent 1, so this is 1, let's say 1, well, it'll be up here. 10 times 1, it'll be 50. So at that point, so it's going to go something like for this particular one, I'll move my 1 over. Okay, that's Not the best graph. It just kind of like takes off. And you can basically try to graph this yourself. Try with the graphing calculator. The graph, let's say, of the same or some, like, let's say some other one, and just see what it looks like. So you can use Google Desmos to graph other ones. But you see it kind of takes off. So, okay. So because the graphs of like these exponential growth, they don't really provide sufficient visual information. So we can take the log, and this helps us understand, regraph it essentially using the log. So the advantage of this procedure is that if this function with this exponential growth, then the log of f is a linear function. We know if we take the log of that function, and it's sort of like the composite in a sense. We have the exponential function, and then we plug it into the log function, and this gives us a linear function. So we feed the exponential function into the log function. And this will give us a linear function, which is actually advantageous versus graphing this exponential function. Let's see an example. Previously, our example was f of x is equal to 5 times 10 to the power x. Let's take the log of this. Taking a log, and we like base 10. So we're going to obtain log 5 times 10 to the power x. Okay. Now we know how to separate this out. This is why I kind of reviewed logs with you. So this would be log 5 plus this log 10 to the exponent x. Now we know what to do. Log 5 plus, we can bring down this x in front, times log 10. But we know what is this log 10? I'll squiggle over here. Log, we assume it's base 10. What does this equal? So it's 10 to some exponent is equal to 10, implies this is equal to, yes? Right, 1, perfect. So this is equal to 1 times our x plus log of 5. And we can rewrite this as x plus log 5. Oops. Getting ahead of myself. So it's x, and we can compute this number with a calculator. So this is approximately equal 0.7. So let's say plus 0.7. So this is a linear function which we've studied before. So we could graph this. That's a little graph over here. So it's up 0.71. Let's say this. And it's a straight line. So this is just that graph transformation. So we took something that was a little difficult to graph, and we converted it to a log, and it's a linear graph, so it's much easier to graph. This is what I noticed when I was looking when the pandemic began. Some graphs actually were because exponentials, and some were logs. They had converted the data over to try to analyze it. I think from the John Hopkins, anyone go to that map tracker at the beginning? Watch what happens. Okay. Anyways, let's move on. So we can see how to use these exponential growth functions. Let's look at this example. So suppose f is a function with exponential growth, such that at this point, 2, plugging it into this function equals 3. At 5, plugging it into this exponential function equals 7. Find a formula for f of x. And the formula is going to be of this particular form, of c times b to this exponent x, and then evaluate it at 17. Okay. So we want it, again, just to repeat, f of x to be of this particular form. And so f at 2 is equal to 3. So of this particular form, that means CB, the exponent 2, because x is 2, is equal to 3. And at f equals 5, f at 5, when x equals 5, this is equal to 7. This means c times b to the exponent 5 is equal to 7. Okay. So we're going to set up something. So we have, let's say, this first one, or CB 5 equals 7, and this second part. I'm just rearranging it. Doesn't matter. So we can take, and you could do it either way. And just let's divide both sides of the first equation. So 1 by 3. I'll write it here. So CB, exponent 5 divide 7. I'm going to divide both sides by 3. And then you see that 3 by part 2 here is equal to CB squared. So we can just substitute that in. And you can do it different ways. You could divide both sides by CB squared. color code it. This is because CB squared equals 3. So this implies our B, because the C's cancel, as you can see, this and this will cancel. B to the exponent 3 is equal to 7 over 3. Then you can take the cube root and get B is equal to 3 root 7 over 3. And then you could calculate this with a calculator, get 1.33. So that's part of it. I have to write over here. So we just found what B is in this, but we still have to find what C is. So we have with B is approximately equal to 1.33. So now using part 2 here, we can find the other part. C times 1 point, because part 2 is C, B squared equals 3. We have B equals 1.33 squared equals 3. And then we just rearrange and solve for our C by isolating it. This is approximately equal 1.7. So therefore, we found our function. So it's approximately equal to 1.7 times 1.33 exponent x. So then f at 7, we could evaluate, or 17, we can evaluate this. This is approximately equal to 216.7. So here is our function. So we determine the formula for this growth function at those points. So population growth. Who likes bacteria? I would say nobody. That's the answer I would give. So we know that the, so what is known in terms of research, populations of various bacteria actually exhibit this exponential growth. So remember the exponential growth is this, f of x equals c times b to the exponent x. This is our exponential growth. So suppose you have a colony of bacteria in a petri dish that has 700 cells. So I'm going to draw a picture. 700 cells at 1 p.m. These bacteria reproduce at a rate that leads to a doubling every 3 hours. So 3 hours later, so at 4 p.m., we have 2 times 700. And then at 7 p.m., we're going to have 2 times 2 times 700, which is 2 to the exponent 2 times 700 of these. So what happens at 9 p.m.? This isn't essentially 3 hours later. So this is 3 hours. This is 3 hours. This is not, this is 2 hours. So what happens there? So this is the same idea, similar to radioactive decay. So essentially here, let me go back. This would be 3, 6, 7, 8. So this is 8 hours later. What happens 8 hours later is the question. So in T hours, there is going to be T divided by 3 doubling periods. I hope you kind of see that. So many hours later, so let's say if it were 6 hours, it'd be 6 divided by 3. So there would be 2 doubling periods. So there would be your time divided by your how long it takes for it to double. So every 3 hours. You can kind of see it by like analyzing the picture. So the number of cells increased by this factor is 2 to the exponent T divided by 3, because that's what's happening in the picture. It's 2 to this exponent. Here it's perfect, like at 7 p.m. it's perfect, but here it's not. So it's going to be that factor of whatever the time is divided by 3. So after T hours, there should be this many bacteria cells. So in this particular, so 9 minus 1 equals 8 is the amount of hours. So in 8 hours, there are 8 divided by 3 doubling periods. So there will be 700 times 2 to the exponent 8 divided by 3 bacteria at 9 p.m. So this is approximately equal to 4,445 bacteria. And this is just thought as an estimate rather than the exact count. I'll just conclude this part. So these functions with this exponential growth often provide the best models for population growth for a limited time period. We can essentially derive like this nice formula from the last example. So this exponential growth and doubling. So if a population doubles, let's say every D time units, then the function, this function can be modeled by F or P, whatever you wish. This population growth is given by this function. So previously, this was their initial population, was our P naught, which was 700. Let me use a different color. So this was 700. Our initial D was our time units. So that was, in our example, was 3 hours. Our initial time, T naught, was 1 p.m. And we were looking at what is the time here at 9 p.m. And this is a bit doubles with the 2. And you can see how like this applied to essentially the last example. So the world population is also approximated by this exponential growth. Recording. So here in this particular, so we're going to apply that formula, that same logic, that essentially finds the formula for the world population between 1950 and 2000. Using a formula, estimate the world population in 1955. And we have like this particular data that at the initial time of 1950, the population, the initial population, I like P naught, I call it like for the initial population, we use that in physics, 2.56. And the days, or not the days, that would be too much, sorry, but the amount of time it doubles is 40 years. So years. Okay, so we're just going to apply that formula. So P naught times 2, so the exponent, T minus T naught divided by RD. So it's 2.56. So the exponent 2 T minus 950 divided by 40. Okay, and the years match. Okay, so that is essentially, we found our formula. Now, then at the specific value at P equals 1955, this is approximately equal to 256 billion times 2 to the exponent 1955 subtract 1950 divided by 40. So this is approximately equal to 2.56 billion people initially times this exponential. So 2 to the power 5 divided by 40. You could reduce this 2.56 times 2 to the power 1/8. And you could get a calculator if you wish. So this is 2.79 billion. And of course, we could compare this if we wish, this estimate to the actual population. And this was the population during that particular period. So compare it to 1955. I would just like look this up using probably Google. Just ask Google for the actual population. Usually there's world data on this. Now the next topic, compound interest. So the computation of compound interest also involves a function with exponential growth. Before jumping right into compound interest, we first learn about simple interest. So simple interest is just interest paid on the original amount of money only first. Compound interest is interest paid on your interest. So there's a difference between the two cases. So first we're going to look at compound interest. So suppose you deposit $8,000 in a bank account that pays supposedly 5% annual interest. I'm not sure if these numbers are realistic today, unfortunately. So we have this principal, P for principal, is $8,000. That's the initial amount. And we have a rate of return of 0.05, which is 5%. And this is annually, which means like yearly. So so what is the question? So assume that the bank pays interest once per year at the end of the year, and that each year you place the interest in a cookie jar for safekeeping. So you take that money and you put it in a cookie jar. So this is the idea of simple interest versus compounding interest. The interest goes in a cookie jar. How much will you have? The original amount plus interest at the end of 2 years. How much? So after 2 years. So we can kind of create like a bit of a sequence in our idea. So after 1 year, we're going to have $8,000 plus that $8,000 times that rate, 0.05. So this is 400. So you're going to be left with $8,400 after 1 year. Makes sense. Okay. After 2 years. Well, we're going to have that original amount, $8,000, plus that amount. So I'll write it out this way. Plus the interest from the, okay. Plus the 400 from the previous year, plus the next 400 that we'll get, which is this amount. So it's going to be 8,000 plus 400 from this part previously, plus this part. So we're going to get 8,800. Because remember that amount goes in a cookie jar after 1 year. That's the idea of the simple interest. Which it's not really that practical, but okay. So after 2 years, we're basically going to get 800 plus this t, the time, like 1 year, 2 years. This was 2, 1, 2, times our 400. So this is our 400, we got it from our rate, times our principal. Oops. Sorry. Our rate here, times our principal, times our t, plus our 800. Because here you see, this part here be 2 times 400 And we could, this 400, you got it from 8,000, this principal times our rate. So this is our time times our principal times our rate. Do you see it? Wait. So essentially, you can derive a formula with simple annual interest. So if we have interest is paid once per year at an annual interest rate, or with no interest paid on the interest. So we don't get interest on our money, essentially. This is called simple interest. And after 2 years, at this initial amount P, called the principal, it grows by this formula. So the principal plus the rate times the principal times our time. We can factor out the P if we wish, and we get essentially like this formula, P times bracket 1 plus RT in bracket. So that is the simple interest formula. Now we're going to look at compound interest. So this is basically earning interest on your interest. So you're earning money on your money. So it's a little bit more interesting. So suppose that you have 8,000 in the bank account that pays 5% annual interest. And assume the bank pays interest once per year at the end of the year, and that each year the interest is deposited in your bank account. So how much will you have at the end of 1 year, 2 years, and 2 years? So we have the principal is equal to $8,000. We have our rate, it's equal to 0.05. So at the end of 1 year, the first year, you're going to have the principal plus the rate times the principal times the time, like before. It's going to be the same number like we did before. $840. What about at the end of the second year? Okay, so at the end of the first year, what do we have? We have at the end, we're going to have, and I'm just writing it out, the formula is 8,000 plus 0.5 times that 8,000. So that was at the end of the first year. And then we take that amount and then we're going to earn interest on that amount. So at the end of the second year, we're going to have so that period from, let me write it out first. So from the second to the third year, you're going to have that initial amount plus that rate, plus you're going to get that interest that you earned, this amount, times that rate. I'll just put R for the rate. And then we can write this all out. and R is 0.05. Okay. Now, you could factor out the 8,000 in front. And you're left with 1 plus 0.05. And then you could actually factor this out twice and you get it to the exponent 2. I can show you, it's a bit more complex. It's not as, you factor it out kind of twice, like, because you're going to have this and then you're also going to have this. So it comes out twice. So that's why it's exponent 2. And then we calculate this, 8820. So that's the end of 2 years. So you kind of can see, okay, well, we have $8,820. But back here, when we did simple interest, we had $8,800. So when we compound it, we have $20 more, essentially, is the idea. So, and you can see why this is kind of from here to here, why that's true, if you wish. So we derive a formula for compound interest once per year. So interest is compounded yearly with a particular interest rate, R, by like this formula. So P is our principal times 1 plus R to the exponent T. So this is exponential. So what happens? Let's just like circle this number. So often interest is, could be compounded more than once per year. Let's say you pay your mortgage or a loan, right? Most of you might want to be homeowners one day. This is an idea, you're paying interest and it's compounded, or your car payment, etc. It's compounded, that interest that you owe, it's compounded, etc. So in the next example, interest will be paid and compounded twice per year rather than once per year. And this means that instead of 5% interest being paid at the end of each year, the interest comes as two payments of 2.5% each year, with the 2.5% interest payments made at the end of 6 months. So you get like a certain principle. Oops. And then you get a principal plus the principal times 0.025. And then the next one, so that's in 6 months. So let's say 6 months later. And this is another 6 months later. What happens? So we get that amount times the principal times 0.05 plus that amount plus 0.025 times that interest. So we're it's compounded on that amount. So here we get our amount, our interest. Here we get that amount plus that interest on that amount. So suppose you deposit again $8,000 at the end of 6 months. What do you have? You're going to have 8,000 plus 8,000 times 0.05 divided by 2. which is 8,020 at the end of the 12-month period. We're going to have 8,000 plus the 8,000 times 0.05 divided by 2, plus this amount. Times that rate. So it's the same thing as before. You get 8,200 plus 8,200 times 0.05 divided by 2. Calculate this, and we get $8,405. So the formula that we kind of just have seen here, we're essentially taking the principal times 1 plus the rate, dividing it by 2 to the exponent 2, where our time here is 1, and this is just 1 year. Okay. So we can reach this following formula for compound interest 2 times per year. Essentially, it's what I just wrote. There's a 2 here and a 2 here. And then we can extend this idea for n, 12, and monthly periods. So it's compounded every month. Instead of the 2, it would be 12. So more frequent compound periods, you notice a pattern, leads to essentially more money earned on your money. So it's good to always have this compounding. So for example, here, like you could call this as a function essentially t. So this is compound interest n times per year. It's equal to the principal times 1 plus r divided by n. That compounding period is n, to the exponent n times t. So t would be your time horizon, like 1 year, etc. So let me write a little note. So it's n times t because compounding occurs n times per year. So, and basically in t years, there are n times t compounding years. Which is periods. So this is like how many times this amount keeps getting compounded, n times t. So it keeps growing. And you notice that this is basically an exponential function. Growth function. It's of the form as CB to the exponent X or something like that. It's very similar to that. Okay, so suppose you have a bank account. Again, starting off with our principal is $8,000. And suppose we get a rate of 0.05. And our compound periods are 12. So our n is equal to 12 times. How much will the bank will be in the bank account after 3 years? So after 3 years, how much do we have? So after 3 years, we can apply this formula, 1 plus r divided by n, exponent n times t. So let's apply it. So it's 8,000 times 1 plus 0.05 divided by, or 12, times 12 times 3. So this is approximately equal, you have to use a calculator, 9,292. Now you could also compare, if you wish, this to what you would have if you used simple interest for 3 years, same time frame. And which one would you prefer to use, right? Like if you had a choice, like which would you prefer to compound simple, or would you prefer use simple interest or use a compounding interest, make money on your money? Compounding. And which time frame would you take n? Would you rather take n be 2 times per year or 12 or monthly? Yeah, or daily even, right? So it's about making those smart choices. So bank accounts. So that's good. So E and natural logs. So in this section, we learn how to estimate certain areas. So for, let's say, positive numbers, B and C, with B being less than C, we can write this thing called this area. So in this way. So the area of 1 over x, this function, from B to C, I'm just going to draw a sketch. Sketch says 1,000 words. So we have this function 1 over x, and between these points, B and C, we can draw like these lines. This is the function 1 over x. And the area is the shaded area underneath that curve. So this is that area. Area of this region is denoted by this thing called area 1 over x BC. And it relates to something in calculus. So this thing called this area is not so important. It's more about the idea that I'm trying to give to you guys. But basically you have a function from a particular point from B to C. That area under the curve is denoted by this, let's say. Now show that this area, let's again draw a picture, is less than 1 in this particular example. Try to draw this as well as we can. So from, let's say, 1 to 2, So this area under this curve is less than 1. So this is a basic kind of idea. It's useful and powerful idea if you take calculus course. So, and let's say like this particular point here is 1. So it's not drawn perfectly. So this point here is 1, 1. This point here should be 2.5 for this function y equals 1 over x. This point might be a little higher, yeah. So we're going to claim that the area of this region is less than 1. So we could draw a box, sort of, and we would see that this part here is 1, and this part here is 1. So we can just simply observe, by observing this carefully, this is going to be bigger than the area underneath the curve. So we can observe this new purplish idea. So we observe that this red, or this kind of pinkish region basically is a square with length 1. Length and width both are 1. So its area 1 squared is equal to 1. So that's the area of this purple. But this is clearly less than the purple. So I'll just write down some notes. So the blue area is smaller, of course, than the pink area. And they're not equal. So therefore, this concludes so that area of 1 over x, the area underneath that curve from 1 to 2 has to be less than 1. Okay. What about this? So show that this area, same function, 1 over x, between 1 to 3 is actually greater than 1. And so this means, let's just draw like a little sketch over here. So 1 to 3, this function. Here's our 2. it's a little difficult. You should try to draw them as exactly as possible. So this area, and as we notice, it's 3 minus 2, or 3, sorry, 3 minus 1. Got the wrong part there. It's 2, so this part here is 2. And we want to, the question says, placing 8 rectangles, each with the same size base inside the enclosed region. So we wish 8 rectangles. Each rectangle has this base. So there's 8 of them. There's the side, it's 2 divided by 8. It's going to be 1/4. It's going to be the base. So we can draw another picture. We have to take our time to draw this as nicely as possible. So we find the areas of the rectangles. So let's draw it carefully. Actually, sorry. So this goes from 1, I'm just drawing the picture, 1 to 3. In the middle here is 2. So, and then we can draw equal parts. So this is going to be 5/4. This is going to be 6/4. 3/2. This is 7/4. 2 is the same as 8/4. Same thing. 9/4. 10/4. 11/4. So we have 8 equal parts. So you just basically divide that area into 8 rectangles in a sense. And we know the function is 1/x. So at this point, or no, when x equals 5/4, this value here is going to be, this is 5/4. This is going to be 1/5/4. So then the height of this triangle right here, 1/5/4, the height is then therefore 4/5. And the next one. So this is 3/2, this height, this particular value. Three over 2 is 1/3/2, which is 3/2 and 2/3. So that's this height, 2/3. These rectangles. And the width, which we just found from over here on this side, was 1/4. So like these widths are 1/4, 1/4. And we could continue on. I'll just make a little note that this is basically the height, which I just wrote. Height of the first rectangle. Okay. So we want to find the area of the first rectangle. So what is the area of the first rectangle? Anyone? Have I lost you with rectangles? Sorry. So the area was just length times width area, right? Length times width. So it's 4/5 times 1/4. So it's, sorry? Close, 4/5 times 1/4. Yeah, right. So the area of the first rectangle is this 4/5, whoops. So that's the height, times 1/4, which is equal to 1/5. This was the height, and this was the base. We can extend this, so the area of the second triangle, or why did I say rectangle? Is 2/3. Let's go back. So it's, the height is 2/3 and the base is 1/4. So we can compute that and we got 1/6. Again, this is the height and this is the base. So we can do this procedure essentially. So just make a summary. So doing the same procedure. For each of these. So for all the 8 rectangles that we have, we find the areas. So, and then the sum, so we add them up, of the areas of these 8. In this case, there are 8 rectangles. Is, and like, let's say we compute it, it's 2, 8, this horrible number. And this is greater than 1. So this means the rectangle, because this is back to the picture, this is less than actually the function. You see it's smaller than. It's like a lower bound. It's less than the actual function by looking at the picture. We didn't draw it the other way. So the rectangles are basically all, are all inside this, the blue region. or the function, whatever you want to say. So that area is therefore, and just 1 over x to 1 over 3. This is greater than this specific number. Which is greater than 1. So we basically found this value, and this was called the lower bound, with 8 rectangles. And this number is approximately equal to 1.0199. So I'll just conclude it. You can take more and more values, which I'll show you next class.